I am recording not your pictures, just your voices. So just understand that I am recording this, but I'm not recording any of your pictures or your videos that are shown. So looking at number 5. Number 5 was a great problem because it has these wonderful fractions. They all actually were great problems because they have wonderful fractions. And there's a couple of different ways that you could probably approach these problems, and it just depends on what you're thinking about first. I look at it and I see fractions, and generally I like to get rid of fractions. So if you wanted to get rid of the fractions in number 5, what would you do to eliminate the fractions first in this problem? And you can just use the raise hand feature. I'll unmute you and then you can answer. But like if I wanted to eliminate the fractions in this problem, how can I eliminate them so that they wouldn't be there? Anyone have an idea? Right. Jen, what do you think? How would you eliminate the fractions from this problem?
Couldn't you multiply both sides by 5
Yeah.
since it's the least common denominator?
Excellent, nice. Good terminology too. So multiply both sides by 5. There's a quantity on the left side, so we would have to multiply that whole quantity by 5. On the right side, the 7/5 fraction is already being multiplied by a quantity, so I only need to multiply the 7/5 by 5. And again, that's because that quantity is already in parentheses. That whole thing is being multiplied by 7/5. So on the left, we need to distribute through. We get a 5x. And then 5 times 3 is 15. When we divide that by 5, we get 3. On the other side, the x plus 1 stays in parentheses. And then we would multiply 5 times 7/5. Well, 5 times 7 is 35. And when we divide that by 5, we go back down to the 7. So this is what the first step would look like. And then we don't have fractions to worry about. I'm also just going to distribute that 7 through the parentheses. So Grant, what would you do next to continue to solve this? Now it's a linear equation. We don't have any fractions.
You would subtract 5x, and then you could subtract the 7 from the other side of the equation.
And you end up with?
2x equals -4.
So x is?
-2.
Perfect, nice. So eliminate the fraction first by using the least common denominator as Jen stated, and then just get those x's on one side, variable in the other, and isolate that variable. Any questions on that? All right, so we're going to go down to the most commonly asked question, and that was the completing the square problems. And I picked number 2, the one in the middle. It has a GCF, so it's a good one to look at. We kind of have to do a couple of things first to organize the information. But when you're completing the square, you want to have the C term on the other side, and I want the A term. So that's kind of how we want it to look. So we want the AX squared, the BX on one side, and the C term on the other. That C term is not a perfect square. It doesn't deal with the process of completing the square. So we always want to isolate that, take it to the other side. So if we kind of rearrange things first, we would have the 6x squared. I'm going to add the 12x, take the 48 to the other side. So just getting it into the format of how it should look to complete the square. That would be the first step. What would the second step be? So Peter, what would the second step be?
It would be to take out a 6 from the left side of the equation.
Right, so in order to complete the square, the coefficient of the x squared has to be a 1. And that's just the process of completing the square, because that 6 isn't a perfect square. So we're going to factor out the 6 from the left side. I'm putting parentheses, leaving a little space. Completing the square means we're going to add or insert a number that is a perfect square into this problem. Peter, do you know how we find that value that we would insert into the problem?
Yeah, you take b divided by 2 and then square it.
Right. And the b value that you're using is this 2. So we took the 6 out. We're no longer using that quantity above. We took the 6 out, and we're going to use the b, which is 2, divided by 2, and you square that. 2 divided by 2 is 1. 1 squared is also 1. There's a little trick, though, when you place the number on the other side. Does anybody know what that trick is? What do you have to remember to do when you place the number on the other side of the equation? Jen, what do you have to do to place the number on the other side of the equation?
You have to multiply a 6 back in since we took it out on the other side.
Nice. So I can't just add a 1 on the other side. Equations have to be equivalent. So we have to multiply that 6 with the 1 so that we're adding a 6 to the other side. And that's to keep the two sides equivalent. So we took a 6 out. That 1 is still in parentheses being multiplied by 6. And then we factor this. So now it's a perfect square, and it would factor as x plus 1 quantity squared, because 1 is a perfect square. 1 times 1 is 1. So x squared plus 2x plus 1 factors as x plus 1 quantity squared. On the other side, we're just adding the 48 and the 6 together. So completing the square part is done. We actually will use this process in chapters 2, 10, and a little bit in 11. So it's going to kind of spiral in a little bit for us throughout the year. And we'll be using it to complete the square to get equations in a specific form, not necessarily to always solve. But this does say to solve the equation. So now that we're solving, we're trying to isolate the variable. So I would want to get rid of the 6. When I have a quantity squared, I would then take the square root of both sides. So the goal is to isolate that quantity, or we're trying to solve for x, so we're getting rid of the 6 in the front first. We're taking the square root of both sides so that we just have x plus 1, because we eliminated the square by taking the square root. And then on the other side, we have the square root of 9. Jack, what's the square root of 9?
That would be 3.
And what goes in front of that 3? Anytime we take a square root of a number and we're solving for x.
A positive, negative.
Right, a plus or minus. And that's the little trick that you can't forget. If we're solving for x squared, there are 2 solutions every time we solve for x squared. So one solution would be equal to the positive 3. The second solution is equal to the negative 3. So anytime we're solving for x squared, there should always be 2 answers. Remember, this graph is a parabola. So it has a left and a right side. It's going to have an answer on the left and the right. So one answer is a 2, and then the other answer would be a negative 4. Questions on that process? Okay. Again, this is something that we will continue to talk about and go over. We'll do a quick review every time we approach the concept again. Looking at the next group of problems, there were 4 different questions on this factoring group. So this was part 4, where it says factor by grouping and using perfect cubes. And you can see I have 4 different questions circled here. We did a lot of factoring throughout the year last year. Chapter 5 is when we really got into the higher power factoring, where we were factoring with like x to the 5th, x to the 6th. I think there were a couple that maybe even had x to the 9th on that one factoring worksheet. So each one of these kind of uses a couple of methods of factoring. So it's not just one method once the powers get larger. If you look at, we're going to start on number 3. Any suggestions about where to start first for number 3? Grant, what do you think?
I think you should divide or take out x to the third from
Yeah.
both numbers.
Take out an x to the third, definitely. What else could we take out besides x to the third?
Divide by 4, x to the third is what I should have said.
That's okay. No worries. So when you take that out, Grant, what do you get?
You get x to the fourth minus 16.
Yeah, that's perfect.
Right?
Yep, that's right. Nice. So a GCF would be the first step to factor this. And then after you take that GCF out, now we have x to the fourth minus 16. So now we have to continue to factor it. So again, I said multiple steps here. What would the next thing be that you'd want to do to get this to factor? Peter, what do you think?
You would take the x to the fourth minus 16, and you could make it in one parenthesis x squared plus 4, and then another x squared minus 4.
Yeah, do you know what that process or what that type of factoring is called? What's special about the 16?
No, it's a square root.
Yeah, it's a square root. So it's called the difference of
Or it's a,
squares. Yeah, perfect squares, difference. So you can only factor it because it's a difference and they're both perfect squares. All right, so we first took out a GCF and then we used perfect squares. If you look at the answer, before you move on to the next problem, ask yourself, is there any other factoring you can do to solve the problem or to reduce the problem? So is there any other factoring that we can do here? Jack, what do you think?
You can factor the x squared minus 4 to x plus 2 and x minus 2.
Right. Oops. So that x squared minus 4 is also a perfect square, a difference of perfect squares, and you can factor that. Jack, why can we not factor the x squared plus 4?
Because it's not a difference of squares.
Excellent. Yeah, so it's not a difference. It has a plus sign, so it's a sum. So a lot of factoring there. GCF, and then 2 problems were the difference of perfect squares. So we're going to move down to number 5. And we'll look at that one as well. I'm noticing right away, I'm seeing that we have a power of 4. But I also noticed that they're all divisible by 5. So GCF first. And that's the first question. Anytime you're factoring, is there a GCF? Right off the bat, every factoring problem, that should be the first question you ask yourself. So I know they all have a 5 in common, but that's all they have in common. So I have to keep the large power of x to the 4th, dividing by 5 here, and then that would be my new expression inside. So x to the 4th minus 4x squared, and then minus 5. So it looks like this is that trinomial form. So this is similar to ax squared plus bx plus c, but it's ax to the 4th, bx squared, and then still a c. How would you factor this? So what would we do next? So think about factoring a trinomial. Traditionally, how do you factor a trinomial? Jen, what do you think?
You used AC grouping.
Yeah, we use AC grouping. So Jen, we have a -5. What 2 numbers multiply to be -5?
1 and -5.
Yeah. And then what would you do with those numbers, Jen?
You have to put them together to equal -4.
Right. So how would that look?
X to the 4th minus 5x squared plus 1x squared minus 5.
Perfect. And if you have them flipped, that's okay too. So if you have plus 1x squared minus 5x squared and then minus 5, that's all right as well. So grouping means I'm going to group the first pair together and take out what they have in common. They both have an x squared. Looking at the second pair, they don't have anything in common besides a 1. I'm going to write that one in front so that I can then see the two values that I'm going to group together. So I took out what each pair had in common, and then remember, factor by grouping. You group the two quantities in front of the parenthesis that is the same together. So I'm going to group x squared plus 1, grouping those together, and then I'm grouping x squared minus 5. And then that last thing that sometimes gets forgotten, there was a GCF, so we have to take the GCF and bring it down. So this is factoring a trinomial that isn't just x squared, but instead is x to the 4th, but the process is exactly the same. So if we go to number 7, this one is a little different from the two that we've seen, so it's kind of nice to see a couple different types. The first one we use GCF, and then we use difference of perfect squares. In number 5, we use GCF, and then we use that trinomial AC grouping. Number 7 is going to be another way of factoring, and again, GCF, noticing they both have an x in common. I know I can take that out, but 64 and 125, they don't have anything in common. So what's special about the numbers 64 and 125? Think about the kind of numbers these are. What would be special about them? Does anybody have an idea? Jack?
They're both perfect cubes.
Yeah, they're both perfect cubes. So this is that perfect cube pattern. So they are both perfect cubes. It looks like a cubed plus b cubed. That's how it's set up. Jack, what is the cube root of 64?
4.
Yeah, and it has an x next to it, so we'll put that x. It was 64x cubed, so the a term would be 4x. Jack, what's the cube root of 125?
5.
Excellent. So when you factor this, there is a pattern. So this is a pattern way of factoring, and it's a same sign b. Well, it started with a plus in the problem, so I have a plus. And then it's a squared. The opposite sign has to switch to a subtraction. A times b, always addition, always plus at the end, and then b squared. So that's the pattern. So once you know what your a and your b values are, you plug them into the pattern. So a is 4x, same sign b, which is 5. So I'm just plugging them into the pattern. And then I have to take a and square it. Well, you're squaring all of this. So I have to square the 4, and I have to square the x. That's like something that people forget, so make sure you square both. We have the opposite sign, which is a minus. And then it says take a times b. So I'm taking a and multiplying it by b. That's 20. Always plus, and then the last part is b squared. Well, 5 squared is 25. And then it's factored. The last part I have to remember is that GCF, don't forget to write it in the final answer. So we factored this one with perfect cubes. Questions? So the very last one, I had a mistake on the answer key, which I probably should have been paying more attention when I was writing the stuff down. But this problem, I think a lot of you may have gotten correct, but you weren't sure because Mrs. Kane had the wrong answer on the answer key. So I would factor out a 1/4, and then this answer and the answer to number 3 is going to be almost identical. So I would have 1/4 x squared plus 4, and then x plus 2 and x minus 2. So this worksheet is due this evening at 10 o'clock. If you find that you have other questions, I have a Zoom session at 3:10 today that you can feel free to join, and it'll be open, or feel free to email me questions, and I'll get back to you and hopefully answer some of those problems. But make sure that you're submitting it to Google Classroom. So if you have problems sending it from Notability to Google Classroom, save it to your Google Drive first. Sometimes there's glitches with Notability, but just save it to your Google Drive and then upload it into Google Classroom from your Google Drive. Questions? Okay, so we're going to kind of flip directions here. If you can take out the prerequisite notes packet, this is what we're going to spend the next 2 weeks on. So we're going to talk about like some prerequisite topics. Some of it will be some of the problems that were in that pre-course review, and kind of based off of the problems that I'm noticing. We might go through one section a little more thoroughly than the other. Others we might just breeze through just because there weren't a lot of questions to go over. So again, see if you can find the prerequisite topics packet. Is everybody okay? Still with me? No questions? Okay, good. So today we're going to just talk about 3 short little concepts. The first being the Cartesian plane, and that's a really fancy name for something that you use pretty frequently. We're going to review the distance formula and the midpoint formula. Sounds a little bit like geometry, but they actually do get used in all math, so we might be interested in finding the difference between 2 points in order to find the shape of a figure, the volume of a figure. It kind of depends on what we're working with, the area, but we will be using those formulas, so just a little review here. But does anybody know what this fancy word means, the Cartesian plane? What does that really mean in basic terms? Sounds really fancy, but it isn't. Jack, what do you think?
I'm gonna hazard a wild guess and say the graph.
Yeah, it is. That's a fancy name for our graph. And I'm going to say, we'll say a graph with the XY axis. So a guy named Rene Descartes, he was the one who created the Cartesian plane, the XY axis. So he's a mathematician, and he was credited for like starting this XY axis graphing system. But fancy name, he's French. Cartesian is French. So he came up with that name. So in the examples below, there are 3 examples here where you're asked to determine the quadrant in which the point would be located. So remember, the Cartesian plane has 4 quadrants. Remember, they go counterclockwise. So essentially, you have to think about what restrictions are you given, and where would that then place those 2 points? Or the ordered pair, not 2 points, but the x and y value. So here for the first one, it says x is less than 0. So think about your x value that goes left and right. It's less than 0. But y is greater than 0. So what quadrant would that point be located in? So if x is less than 0, and if you need to draw yourself a little diagram, that's this side here. That's where x is less than 0 on the left side. Y is greater than 0. Well, the only place where y is greater than 0 on the left is in quadrant 2. That's quadrant 2. There really isn't much work you can show for that, unless you draw yourself a little diagram like I just did. So if we look at letter B, we have x equals 5 and y is less than 0. So x is 5, y is less than 0. Where would this point be located, Jack?
That would be quadrant 1. Or wait, no, quadrant 4.
Quadrant 4, right. So x is 5 somewhere over here, but it's 5 on that whole line. And then less than 0 will be quadrant 4. The last one, this one's a little trickier. We want x divided by y to be less than 0. So think about that. Why would a fraction be less than 0? What has to happen if a fraction is less than 0? Peter, what do you think?
It could be in quadrant 2, 3, or 4.
So he said 2, and I heard something else, 4.
And then 3 as well.
So Peter, could it be in quadrant?
Oh, wait, never mind. It couldn't.
Why can't
Never
it be in
mind.
quadrant 3?
Just 2 and 4.
Why can't it be in
Because it'd be a negative divided by a negative, and that would make a positive.
Excellent. Nice job. Good way to catch yourself. So it can be in quadrant 2 because x is negative. We have a negative x value and a positive y value. And a negative divided by a positive is negative. In quadrant 4, we have a positive x value, but a negative y value. A positive divided by a negative is still a negative. Questions on that? All right, so we have 2 more little terms here. So we have our Cartesian plane, and that's like locating points within the plane. And then we have 2 formulas, the distance formula and the midpoint formula. And you may have learned these formulas as far back as pre-algebra. You might have briefly discussed them back in pre-algebra, definitely in geometry. When you were doing, for sure, like the Pythagorean theorem, I think you probably used them then. Does anyone want to take a shot at either of the 2 formulas? And you can give me either one, either distance or midpoint. These are tricky. Jen, what do you think? Which one do you want to give me?
I remember a little bit of the distance formula, isn't
Okay.
it? The square root of x squared plus y squared, and then divided by 2, something like that.
Oh, you're so close. You're very close. I think you were kind of giving me partially the midpoint formula as well. So I'm going to kind of take what you just told me and place it within the midpoint formula.
Okay.
I'm going to erase this a little bit. So the midpoint formula, she gave me a little bit of both. The midpoint adds your x values together and divides it by 2 because you're finding the middle. So essentially we're finding the halfway mark. So, and then it adds your y's together and cuts them in half. So let's go back to that distance. She was kind of on the right track. It definitely has a square root. Grant, do you remember the distance formula?
Isn't there like a plus in front of the nah. I don't remember it.
No, yeah, this one's hard. Jack, what do you think?
I'm going to say x2 plus x1, or yeah, is it x2 plus x1 squared and then
It's actually a
y2 plus y? Oh, it's a minus.
Yeah.
Okay, yeah, that makes sense. And then y2 minus y1 squared.
right. And you can have them flipped either way, as long as you're writing them the same way. So you could have x1 minus x2 quantity squared. You're adding that to the quantity y1 minus y2 quantity squared, or you can flip them around. So you're subtracting the x's, squaring it, subtracting the y's, squaring them, and then adding those 2 quantities together. So this last example here, we have 2 points. It wants us to find the distance between the points and to find the midpoint of the line segment joining the points. So if I want to find the distance, this is like a plug and chug. So we're taking our x values, and again, it doesn't matter which one you start with, but you have to be consistent. So x1, x2, y1, y2. So I could take 1/2 and subtract 1/4. Those are both my x values. And then I would go with -3 and subtract 3/2. So I started with the x1 value and the y1 value. Now, I threw in fractions here because I wanted to give you a little bit of a challenge. I'm going to get a common denominator. So this becomes 2/4. And I do want you to try and keep these answers exact and not write them as decimals. So this is going to be 1/4 squared. I'm going to change the -3 to be -6/2. So -6 minus 3 is -9/2, and then squared. We will work with fractions throughout the entire year. When you square a fraction, you square the top and you square the bottom. So I would square 1/4 and make it 1/16. And remember, order of operations says you square things first. So like we're doing stuff underneath the radical here. And then -9/4 or -9/2, if I square that, the -9 becomes +81, and the 2 becomes a 4. Ugly, really, really looks ugly. And then the last thing I have to do is add those two numbers together. So again, I have to get a common denominator one more time. So I was truly evil here. So I have to multiply the denominator by 4 to make it 16. Anybody know what 81 times 4 is? Peter, what's 81 times 4?
Is it 324?
Yeah, and when you add 1 to that, you get 325. So there's one final thing I could do to this. I could take the square root of just the 16 and make it a 4, and then I could keep the 325 on top. But I don't want a decimal, so just try and keep it as exact as possible. So I'm going to stop there. There are underneath just a reminder with directions about creating a scatter plot. You don't have to do one today, but I just want to kind of have them in this packet for you because I believe at some point throughout the notes that there'll be information about creating a scatter plot, so I put them in there for you. There is a worksheet posted in Google Classroom for today, and it has a couple of problems like this, where you're asked to get the distance or get the midpoint or the Cartesian plane, those couple of problems at the top. There will be a worksheet for you to do, and then there's that daily homework questions form. If you have any questions from the worksheet, fill out that form. But I will see you all tomorrow. Best of luck to you for the rest of your virtual day, and I appreciate all of you coming. Thank you. Have a good one.
Thank you.
Thank you.
Thanks.